Hello everyone, Assalamu alaikum. Welcome back to my channel. If you haven't subscribed yet, just click the button and hit the bell icon so that you can get in touch with my latest content. So this is part 2 of the 3-part series that I'll be uploading today. So we are going to dive deeper into Cadence Virtuoso and create layout for CMOS inverter. So in this particular video, we are actually going to create the layout, and in the next video, we are going to discuss about how to perform DRC and LVS check on the inverter that you have created or any circuit that you have created. So if you are following along in our VLSI lab series, this will build on what we have already learned with schematics and simulations. Now let's move on to the physical design, which is a crucial step in custom IC design. Now layout is the representation of a circuit in terms of planar geometric shapes, for example rectangles, polygons, that shows us the pattern of metal, polysilicon, oxide or diffusion layers that make up the components of the IC. When using the standard process, for example in this lab we are using 90 nanometer process, so the behavior of the final integrated circuit depends significantly on the positions and interconnections of the geometric shapes due to parasitic resistances and capacitances contributed by them. While designing a layout, designer must keep in mind the performance and size criterion. While designing digital circuits, one usually follows an ASIC design flow where the height of the standard cells that are used is the same throughout the cell library, but the widths must vary according to their logical functions and drive strengths. Although we will follow a full custom IC design flow, we will maintain same height, same cell height throughout our library cell. The generated layout must pass a series of checks in a process known as physical verification. The most common checks in this verification process are: number 1, design rule check, DRC; number 2, layout versus schematic, LVS check; and number 3, parasitic extraction and post layout simulation. So we are going to talk about these 3 checks in the next video, but in this video we are going to now design our layout. So let's just go to the Virtuoso layout editor. What you need to do is invoke this Virtuoso layout editor from CIW by executing file, new, and then cell view. The new file form appears. Fill it as it is shown here, like I'm filling. So you need to call in the cell that you created in the previous video, the copied cell. Now the following window for layout editor will appear. On the left hand side of the window, you will find the panel called layers. This panel is divided in 3 main categories, which are layer color, layer name, and layer purpose. Now before starting to design the layout, you need to set the layout display configuration. Execute the following Virtuoso layout editor. So in the options, go to display, or you can also press E on the keyboard. Now the following configuration form will be displayed. You have to set the following parameters only. You just need to set the minor spacing, major spacing, X snap spacing, Y snap spacing, and display levels to stop. That's it. That's all the setting that you need to do. And click OK. Now we are going to build the layout of the inverter. An inverter has an NMOS and a PMOS transistor, as you all know. First we will build an NMOS transistor. Now layout of the NMOS transistor consists of oxide, N implant, contacts, and poly layers. You need to study the rules of these layers and calculate the minimum size of the poly, contact, oxide, and N imp layer to create this NMOS transistor. And these rules can be studied from the technology library that you are using. In this case, I'm using the GPTK090 technology. You can see the rules related to NMOS transistor in the following figure. In addition to studying the NMOS transistor rules, you also need to study the PMOS transistor structure in this specifications. The PMOS transistor consists of oxide, poly, p-imp, contact, and N-well layer. Now you need to study these rules as well and calculate the minimum size of poly, contact, oxide, p-imp, and N-well layer to create this PMOS transistor. These rules are also shown here. The only difference between NMOS and PMOS is that it is surrounded by an N-well. This PMOS is surrounded by an N-well. So the rest of the spacing and width, etc., these rules remain the same. Now we will start building the NMOS and PMOS transistor layout. Look at the LSW and find the current drawing layer. You need to click on the following icon in this Virtuoso layout editor window so that it notifies you anytime you make any violation of a design rule. When clicked, it will show DRD notify on. DRD stands for design rule driven. Now select contact and draw this layer from the layers panel and draw the rectangle of this contact layer using create shape and rectangle, or simply press R on your keyboard. Once you're done, you can press escape to stop creating this rectangle. In a GPTK090 technology, contact layers must be of dimension 0.12 meter by 0.12 meter. So if your rectangle is not of that dimension, don't worry about it. Just click on the rectangle, press Q. In the following window that appears, check if this criterion has been met and change the width or height if required. Now contact to poly spacing must be 0.1 meter in this technology, and the channel length of NMOS or PMOS in our design is 0.1 meter. So we need a minimum spacing of 0.3 meter between the contacts as source and drain. Now press K to invoke the ruler tool. Use it to measure the length whenever needed. This is a very useful tool. To copy, press C. After placing two contacts, the layer looks something like this, and just follow along what I am doing. Now contact to oxide spacing is minimum 0.06 meters, so draw a rectangle of oxide layer so that it covers both the contacts and extends from each side by 0.06 meter. Now while drawing this, you will see the design rule violations when they are committed, while because you have already clicked on that button. So whenever you violate these rules, you will get a warning. So after drawing this oxide layer, the layout should look something like this. Now we will draw an imp layer which must extend from the oxide layer by minimum of 0.14 meter. First draw a rectangle and then extend it to meet the design rules. You can use the stretch rule by pressing S. After drawing this, the layout will look something like this. Now copy it and create another copy of all the layers by selecting all and pressing C. Click on this imp layer of the copy in the upper portion of the layer and press Q to edit properties. Now what you are doing here is just copying this transistor and converting it to a PMOS instead of an NMOS. From this edit rectangle properties, select P-imp layer under the layer options and click OK. And that's it, you have now a PMOS and an NMOS transistor. Now, with more metal layers available in today's silicon process, using the routing approach, such as first metal traverse vertically and second metal traverse horizontally, would be advantageous in standard cell physical design. Using this method, the second layer or metal 2 can be used for power and ground routing over the internal standard cell transistors. In standard cell layout, it is preferable to use first the conducting layer, such as metal 1, as much as possible to make internal connections of NMOS and PMOS transistors. So our cells will have a height of 5 meter, so we need to place two parts, NMOS and PMOS, 2 meters apart, and create a ruler so that the cell height can be checked whenever needed and separation between the NMOS and PMOS can be maintained properly. Now the layout will look something like this after placing this ruler. Next, we need to draw the poly layer by selecting this poly from the layers panel and pressing P to invoke this create path tool. This layer must be of 0.1 meter in width and in between the two contacts extending from the oxide layer by 0.18 meters, at least on both sides. So after placing the poly gate, the layout will look something like this. Don't worry if your widths and heights are not exactly according to the parameters. You can either select the properties, check the properties, and make them according to the given specifications, or uh, for now just make sure that your design looks something like this. We can make them accurate once we perform the DRC check. Now that you know most of the shortcuts and layers, you need to draw the contacts for body terminals for NMOS and PMOS. These portions should consist of contact, oxide, and NIMP. So just keep in mind the TRD notifications for the design rule violations, and you just need to draw something like this. Now connect the drain regions of NMOS and PMOS. Also connect the source of both MOSs to respective body terminals using this metal one layer. Then connect the drains of MOSs using metal one layer. PMOS should be in N-well, so draw an N-well rectangle surrounding both the PMOS and the body contact for PMOS. The layout will look something like this now. Now we have to place the pins. The gate is in poly layer. Let's bring it to metal one layer by extending the poly layer, creating a contact between poly and metal one layer by pressing O to create via and selecting M1POV under the via definition and placing it on the layout like so. Also draw a metal one rectangle on the via because the default metal one rectangle area is less than the required minimum. Now execute create pin to create pins for VDD, ground, and in and out. For in VDD and ground, select input as IO type, as you know, and for out, select output as the IO type. Now draw rectangles on the poly to metal 1 via for in pin, PMOS source to body metal 1 connection for VDD pin, and NMOS source to body connection for for ground pin. For out pin, draw the rectangle on the metal 1 layer connecting the two drains of MOSes. You can also add labels to the pins if required. Not really necessary, but it's helpful to find out the location of the pins. Finally, we will add metal two paths of 0.5 width of power rails and connect them to power nets in metal 1 by using metal 1 to metal 2 via by invoking create via. And your final layout will look something like this. We have gone through the entire process of creating a layout for CMOS inverter. In the next lab, we will find how to perform DRC and LVS check and also find the parasitic extractions and post layout simulations. Thanks for tuning in. If you found this video helpful, make sure to hit the like button, share it with your friends, and don't forget to subscribe for more VLSI content. See you in the next video.